Hello guys, in this video I'm gonna continue with KVL and KCL circuit analysis. So last video we solved with an example, we analyzed the circuit, and I promised you to basically solve it with another solution which is like relatively easier or simpler than the first one. Okay? So I'm gonna remind you with the first solutions that we saw for this circuit in here. So basically the requirement is to find the voltage across the current source of 1.8 milliampere, this one here. And we solve it basically with KVL. So we have two nodes, two loops, loop one and loop two, and and also KCL a little bit, so both at the same time. Okay, now we're gonna solve it only by or again, KCL and KVL, but a lot simpler. Okay, so let's see how we do that. Okay, so first of all, let's look at this point in here or this node, and let's call it V. Okay, that's a node that has three branches, so we can apply KCL. So KCL at point or node V. What this will give us? Again, KCL means the current that is going into the node equal to the current or the sum of the currents is going out of the node. Here, all the current are going out, so I1 plus I2 plus I3 equal to the current going into the node. No currents going into the node, so their sum is zero. Okay, good. Again, I3 is flowing in that branch in here, which is the same branch as the current source 1.8 milliampere, but they are flowing in opposite direction. So basically, I3 is equal to minus 1.8 milliamperes. And again, all the resistances here are in kilo ohm. So, and the current is in milliampere, as you see, guys. So keep it as it is. Don't convert milliamperes to amperes and don't convert kilo ohm to ohms. So you either deal with them both in milliampere and kilo ohm, or deal with them in ohms and amperes. Okay, good. Good. So we know I3. So from that here, we can say that I1, or let's continue. Yeah. So we get I3. Let's check now I2. Where is I2? This is I2 in here. This guy. I2 is flowing in the resistance 3.3 kilo ohms. From that point, which is V, to that point, which is ground. So if a circuit has a ground, that means this point has a zero voltage. So there is a zero here, 0 volt. Okay, and we said last time, even if the circuit doesn't have a ground, you can put a ground. You can check any node, any terminal, any point, any short circuit, and this is zero. Okay, because we always love, the voltage difference across the resistance, not the point voltage. Good. So let's take this branch in here and separate it from the circuit. So this branch has a resistance 3.3 kilo ohms. This point has a voltage called V, we don't know it. This node has a voltage 0, we know it. And I2 is flowing from V to 0. So I2 is equal to I is equal to the voltage across the resistor, divided by the resistor value. The resistor value is 3.3 kilo ohms. Keep it in kilo, the current will be in milli. It's fine. Now, what is the voltage across the resistor? What is the voltage of the resistor? The voltage of the resistor is basically the voltage difference across its terminal. Okay? So the current is flowing in that way, so I'm going to assume the voltage is in that way. So that's positive, that's negative. So the voltage of the resistor is equal to the voltage of the positive terminal minus the voltage of the negative terminal. The voltage of the positive terminal is V. The voltage of the negative terminal is 0. So V minus 0 divided by 3.3. So that's equal to V divided by 3.3. So we also have an equation for I2 in terms of V. Number 3. Now let's look at I1. I1 is flowing. Let's remove first this green stuff. I1 is flowing in that branch like that. In the resistor, it flows from that point to that point, from this terminal on the right to this terminal on the left. I'm gonna assume the voltage of the resistor is 2.2 kilo ohms in that way. That's the voltage. I will not give it a name because we already named this node here V. But we know the voltage is in that direction. So that's the positive and that's the negative. Okay. So what is the voltage of that node? It is V. Why? Because remember, guys, this all is just a short circuit. So all this stuff, all this blue wire has a voltage called V. Okay. Now, what is the voltage of that point? Let's call it point A. Okay, that's really nice. So let's, for A, for voltage VA. Want to know it. Okay, but we're gonna determine it. So let's draw on a side here the battery 9 volt. So we have here a battery or voltage source has a voltage of 9 volt. We said before a battery makes its positive terminal higher in value or higher in voltage than its negative terminal by the amount of the battery. Or a battery can give you voltage difference, can give you a voltage difference between the positive terminal and the negative terminal. So the line, let's call this is VA here, and remember this is 0. We call this is 0 here. This all of that terminal is 0. So we can say 9 volt equal to VA, which is the positive terminal, not minus 0. So 9 equal to VA. So VA is equal to 9. Very nice. So we know VA is equal to 9 volt now. So let's draw that branch by itself. Here we have 2.2 kilo ohms. This point has a voltage V. This point has a voltage 9. And the I1 is flowing like that. And we assumed the voltage like that. Okay? So I1 equal to the voltage difference across the resistance, or the voltage of the resistance, which is the voltage difference across it, which is equal to the positive voltage, which is V, minus the negative voltage, which is negative voltage doesn't mean the voltage is negative. The voltage of the negative terminal, let's call it so. So minus 9 divided by 2.2. So we get also I1. Look now, I3 is constant. That's very good. I2 is a function of V. I1 is also a function of V. So that equation here, this equation, KCL, it has two unknowns before. Now it is had just one unknown, which is V. So let's rewrite it. So let's call it 1. So rewriting equation 1 in terms of V. In terms of V. So let's write it. I1 is V minus 9 divided by 2.2. I2 is V over 3.3. I3 is minus 1.8 milliampere. We can just rewrite 1.8. We know the currents will be in milliamperes, equal to 0. Very good. Now let's have a separation here, and let's continue. So V over 2.2 minus 9 divided by, just simplify it, over 2.2 plus V divided by 3.3 minus 1.8 equal to 0. So V, take V as a common factor from that term and that term. So that will end up 1 divided by 2.2 plus 1 divided by 3.3 minus 9 divided by 2.2 minus 1.8. Okay? Equal to 0. So V 1 divided by 2.2 plus 1 divided by 3.3 equal to 9 divided by 2.2 plus 1.8. So V is equal to uh, 9 divided by 2.2 plus 1.8 divided by 1 divided by 2.2 plus 1 divided by 3.3. I like this. Don't simplify the math until you have the last equation. Then use Desmos, because Desmos you can just write this exactly as it is, as you see here, so you can review easily. So let's do this in Desmos calculator, online calculator. You can find the link in the description. So 1 second to bring it here. Okay, guys, we are back. So we have here the Desmos calculator online. Okay, I have some calculations from previous, and we're gonna calculate this one. Of course you can use your own calculator, that's fine, but I like to use Desmos. Why? I'm gonna show you now. So we have the numerator 9 divided by 2.2 plus 1.8. Put this in a bracket and divide 1 divided by 2.2 plus 1 divided by 3.3. Look, guys, we wrote exactly the same equation in Desmos. This is exactly this one. So you can review easily. So you can track down where is your fault, if there is. Okay? And we see that the voltage is equal to 7.776. We are not done yet. Why? Because the main objective here is not to find V, the voltage of this node, but to find V1, the voltage across the 1.8 milliampere current source. Okay, so for that we have to do KVL. Actually, we can find it without using KVL. How we can do that? Yes, without KVL. I'm gonna do again with something like this or like this. Again, look at I3 now. Okay, so let's go a little bit to the right. I3 is flowing in the 1 kilo ohm resistor like that. Okay, so I'm gonna assume the voltage of the 1 kilo ohm resistor like that. So that's the positive terminal and that's the negative terminal. Again, positive terminal doesn't mean you have a positive voltage. Might be negative, by the way. Negative terminal doesn't mean you have a negative voltage. No, it can be positive, by the way. Okay, positive and negative here means which is bigger than which. So when we say a positive terminal and a negative terminal, that means the positive terminal should have a voltage larger than the negative terminal. Okay, good. So this is I3 flowing in that direction like that, from that point to that point. What is the voltage of that point? It is V, because this is a short circuit, and any point in the short circuit have the same voltage. All the points have the same voltages, which is V in that case. Okay, so that's V. Now, what is the voltage on that terminal? Let's check that one. Okay, let's call it VB. I'm gonna call it VB, or let's use another color. For example, this guy, or green. VB. So let's draw on a side here the current source, the 1.8 milliampere. This point is 0, correct? 0. This point is the ground. And this point, we don't know. We know that the voltage across the current source, which is required, is V1. So when we know the voltage from negative to positive like that is called V1, that means that point, which is VB, higher than 0 by V1. So V1 is equal to VB minus 0. So that means VB is equal to V1. So VB here is equal to V1. Good. So let's now write down or draw down this branch again. This is the 1 kilo ohm. Here we have V, which we know. We just determined 7.776. And that's VB, yeah, I'm sorry, V1, or equal to VB. And I3 is flowing like that. And the voltage is like that. So that's the positive terminal, and that's the negative terminal. So I3 equal to V minus V1 divided by 1 kilo. Don't convert 1 kilo to ohms. Keep it 1, and the current will be in milliamperes. Okay, so now, do we know I3? We don't know the value, but we know it's the equation. I3, if you go back here, I'm sorry, we know the I3, yeah. I3 is equal to minus 1.8 milliampere because it's flowing in the same branch as the current source, but in opposite direction. So it's equal to the current source value, but with minus. So I3 is equal to minus 1.8 milli. So V minus, I'm sorry, V, and what is V? V is, we determine it here, 7.776 minus V1 is equal to minus 1.8. Bring V1 here, bring the 1.8 here. So 7.776 plus 1.8 equal to V1. So V1 is equal to, uh, it is correct, but I'm gonna calculate again because I forgot. So 1.8 plus 7.776. Yes, it's a 9.57, which is the correct value. Let's check against like the previous. So 9.57. 9, yes, 9.57. Of course, you can say 9.574. Here it's 9.976, I believe. Yeah, 6. So they are different in the, that's fine. Don't worry about that. This is just normal, like rounding errors that happens when you use multiple solutions or different solutions for the same example. So that's acceptable. Okay. Usually, at least one should match. I mean, this should match the number just on the right of the decimal point, and the left of the decimal point, and just one here on the left of the decimal point. Okay, one decimal place must match at least. One decimal place at least must match. Okay, guys, that was it. Okay, thank you very much for watching, and see you in another video. Bye bye.